came across a pretty interesting problem here that deals with the Archimedean spiral. So the Archimedean spiral, if you're familiar with polar coordinates, is the graph that you get if you just graph r equals theta. So what that means is that as you increase your angular position around the center of this graph, around the origin, you're also increasing the distance you are from that center simultaneously. And so it's a pretty interesting graph, and what we're going to talk about within this video is we're going to talk about an area calculation of this portion of the Archimedean spiral. So we have the graph of r equals theta, the Archimedean spiral shown from 0 to 3 pi. And what we want to do is we want to determine the area of the shaded region. So this region sits entirely above the x-axis, but we don't want to count this inner loop right here. So we want the area within this outside loop, but outside this. So these sort of polar area calculations are oftentimes a little bit difficult to try to reason through. So I want to try to break it down into chunks here so that we have a little bit of an idea as to why the calculation that needs to be done actually is the one that gets you the area that's shaded. So first off, I have the graph of the Archimedean spiral from 0 to 3 pi shown. So I realize that I'm at the x-axis here, I'm at the x-axis here, I'm at the x-axis here, and I'm at the x-axis here. So based on this shaded region back here, sitting entirely above the x-axis, seems like a logical question for us to try to identify the answer to is for what values of theta is this graph going to actually hit the x-axis? Now on the x-axis, you would know your y-coordinate is 0. So when does y equal 0? Well, if you've done some work with polar coordinates, you know that y is equal to r times sine of theta. I'm putting 0 in for y, and I need to solve this. And I've also put theta, right? This is a graph of r equals theta. I've put theta in place of the r. Now, this is already a factored form of this equation on the right-hand side. It's multiplication. So when you have a multiplication problem with an answer of 0, you simply set the first factor equal to 0. Theta is equal to 0 when theta equals 0. And then set the second factor equal to 0. Sine of theta is going to equal 0 if I'm at one of these locations on the unit circle. So these locations on the unit circle would correspond to the angles 0, pi, 2 pi, 3 pi. Now that list does extend forward, technically also extends backward, but keep in mind what portion of the graph we're considering here. We're considering the stretch from 0 to 3 pi. So we really only need this set of 4 values as the 1, 2, 3, 4 times when this graph crosses the x-axis. So I have a little bit different graph to show on this screen. So it's the Archimedean spiral from 0 to 3 pi is the red graph that you see. Now, the only stretch that you see in red is down here, because what I've done is I've graphed the stretch of the Archimedean spiral from 2 pi to 3 pi in blue, so that overlaps the outer portion from that shaded region that we saw a couple screens ago. And then I've graphed the stretch from 0 to pi. So basically, I just kind of broke it down according to those theta values that we identified as thetas where this graph crossed the x-axis. And so what this tells me is I can find this area in basically 2 separate calculations and subtract the 2 to get that shaded space from a couple screens ago. So I can find the area of the big blue portion, so across the x-axis and outside this blue graph, in one calculation. And then if I subtract off the area of the small inner loop right here that's outlined in green, I'm going to end up with the area of that shaded region, right? Area of the shaded region is the area of the big blue space minus the smaller green space. So how do we find the area from 2 pi to 3 pi? So if you've done some work with polar area calculations, which I'm guessing you have if you're watching this video and you've made it this far in, what you're going to do is you're going to slice your region with sectors. So what I have is I have a sector of this region originating at the origin, working its way out to the polar curve r equals theta. Now, this isn't this is an approximation for the area of that sector because it's technically not truly a sector. This is not a true circle on the outer edge right here. So what I'm doing is I'm approximating the area of this little wedge of the region as if it were a sector. So the area of a sector is 1/2 times your radius squared times whatever the angle that you're spanning through within the circle is. And in this case, it's a tiny, tiny change in the angle theta. Now r in this case is equal to theta, so I've replaced this r with theta squared, right? This is still the graph of that Archimedean spiral that we've seen throughout all the screens within this video. This would just be the area of that one wedge, though, the approximate area of that one wedge. What I want to do is I want to add together the areas of every possible sector, every possible wedge that I can draw from this angle to this angle. This angle here, think about where this x-intercept was, that was at the theta value of 2 pi. So you'll notice I'm adding up all possible sectors areas with a definite integral, starting with my lower limit at 2 pi and ending with my upper limit at 3 pi. So that's going to basically account for every possible sector that I could have drawn that has its bounds from 2 pi to 3 pi. This will give the area of this blue space. If I want to subtract off the area of the green space, I need to do another integral to find the area of the green space. So I'm going to use the same strategy. So I've got a sector drawn here. Again, it's not truly a sector. This is not truly a circle on this outer edge, but I'm approximating the area as if it were a sector. So 1/2 times the radius squared times the tiny change in theta that I'm using to represent this angle. R is once again equal to theta, so I've replaced the R with theta. But then I don't want just the area of that one wedge. I want the area of every possible wedge, every possible sector that I could have drawn within this green region here. Now, this initial spot where the graph was on the x-axis corresponds to a theta value of 0. And then this location here is going to correspond to a theta value of pi. So if I integrate this expression to add together every possible sector, every possible wedge that I could have drawn within this green space here, that'll give me the area of the entire section that we had highlighted in green a couple screens ago. So how does it all come together? Well, I'm going to take the area of this space minus the area of that space. We set this integral up a couple screens ago. We set this integral up on the very last screen. I'm going to need to find the antiderivative of 1/2 theta squared. So I'm going to add 1 to the exponent, divide by the new exponent. The 2 in that denominator turns into a 3 because of that division by, or turns into a 6, excuse me, because of that division by 3. I get the same antiderivative over here. I toss in the upper limit, toss in the lower limit, take a difference on both of these. And then it's just a matter of simplifying a little bit. And if all goes according to plan, you get 3 pi cubed. That's a pretty big answer. Pi cubed, that's roughly 3 cubed. That's roughly 27. Times 3, that's going to give you an answer that's a little bit past 81. So is that a feasible answer to get? Well, the nice thing about these visual problems is you can oftentimes kind of check how valid the result seems by just kind of approximating the area. So if you think about drawing a rectangle around this space here, think about what the dimensions of this rectangle would be. I'm at roughly -6 here, and I'm over at, we'll call it, did I say -6? I'm at roughly +6 here. Sorry about that. +6 here, and I'm at roughly -10 over here. So that's about 16 units across the x-axis. And then I'm working my way up, let's see, 5, 6, 7, 8, roughly 8 units up. So 16 times 8 is definitely going to give me an answer that's pretty well past 81, which is good because I'm not counting the space that's here that's within the rectangle but outside the region. I'm not counting the space here that's inside that rectangle but outside the region, and I'm subtracting off that tiny little sliver that was actually tight into the origin down here. So definitely kind of an interesting problem. Hopefully it makes some sense.